we're going to do an English class today. Syzygy, so that's the word of the day. Spelled, okay, everybody repeat after me. S-Y. It's a great word, syzygy. So it means the nearly straight line configuration of three celestial bodies in a gravitational system. Greek. No, I don't know. I don't think I would be a very good English teacher. I had never heard this word in Spanish, but I had to look it up. En español, syzygia. Have you ever heard this, Laura? Me neither. Syzygia. Okay. This is a good word. I was actually doing my research on this word. If you look it up on Wikipedia, Ralph is right that it is the word that gives you the most points in Scrabble. Maybe it's not the word, but among certain words, maybe the ones with no vowels, it's the one that gives you the most points. And I guess it's the second longest word without vowels in the English language after rhythms. But anyway, so actually another thing I found a lot of interesting things. One thing I knew already, actually. So it's probably fair to say that algebraic combinatorics was born at MIT and largely under the influence of Professor Giancarlo Roda. And he started the combinatorics seminar there, but actually that seminar used to be called Syzygy Street. And then that evolved into the MIT combinatorics seminar. The other thing that I found out is that actually, Atari, I guess some of you know Atari. Maybe some of you are too young to know Atari now. But actually Atari was going to be called syzygy, and originally it was called syzygy, but then they found out that there was a candle company based in some hippie commune in Mendocino called syzygy, and so they couldn't take the name and they had to name themselves Atari. But anyway, so syzygies are the topic of the class today. And by the way, so the most common example of syzygies are eclipses, right? So like a lunar eclipse is when the sun and the moon and the earth line up. Okay. So we're going to talk about syzygies, and well, this is mathematics, so you can forget about nearly now. But we know that Descartes taught us that when 3 points line up, then there's an algebraic equation that corresponds to that, right? In general, I mean, if you have 3 vectors in some vector space, then if the 3 of them are lined up like this, right? So they're supposed to be lined up, then you have an equation describing that, right? Which is that the and it's a linear relation like this, right? Now, depending on, you can kind of do this projectively, not projectively, but the point is that the way that mathematicians think of syzygies is that we think of them as linear relations like this, and we're going to be seeking linear relations today. Okay? And well, as you can imagine, as everything else that we've done recently, this is an application of Gröbner basis. So an application of Gröbner basis is computing syzygies. So the question is this one: given polynomials say G1 up to Gm, compute the syzygies between them. The syzygy module. Okay. If you don't like the word module, don't worry about it too much. We'll talk a little bit more about modules. But this is basically going to be the linear combinations of these polynomials, which are equal to zero, where these a's are polynomials. Okay. So I didn't tell you, but maybe this is the polynomial ring in variables, and so these are just going to be polynomials in those n variables. Okay. This is called the syzygy module of those polynomials. And if you remember what a module is, then think about why that's a module and over what it is a module. And if you don't, then I will remind you in a second about modules. Okay, but so for example, we can do this for two polynomials. We can ask what are all the possible ways of writing polynomial times x squared plus polynomial times xy plus y squared equals 0. Okay. So what's the story? The story, as usual, is that this is going to be a lot easier to do if you have a Gröbner basis. Okay. So this is easier if you start with a Gröbner basis. A Gröbner basis for what? We don't have an ideal yet, right? But if it's a Gröbner basis for the ideal that they generate. Okay, so that's the first point I want to make. But the second point is that this is not such a big restriction, because if you can do this for Gröbner basis, then you can do it for other things as well. So if you know how to do this for Gröbner basis, then you know how to do it. You also know how to do it in other cases. Okay, so that's the plan. First, I will teach you how to do this with Gröbner basis, and then I will teach you how, if you don't have a Gröbner basis, how do you reduce to the case of a Gröbner basis. Okay. So what's the plan? Well, let's first talk about step 1. Okay. And maybe what I will do is, we'll do theory here, but I want to do an example over there. Or maybe we'll do it over here. So keep this example in mind. G1 equals x squared, G2 equals xy plus y squared. Okay. Okay, so what's the first thing you do? Well, the first thing you should do is recall this criterion of Buchberger, which says the following. It says that if we do have a Gröbner basis, then when you compute this polynomial s, gi, gj, and remember that what that polynomial is the polynomial you get by canceling the leading coefficient of these two guys. Okay? So let me write it like this. I'm going to change the notation a little bit this time. So it's something times the first guy minus something times the second guy, where this is exactly what I told you it was last time. Basically, you take the least common multiple of the initial terms of gi and gj, and then you divide by the initial term of gi. And then if you want mji, you just divide by the initial term of gj. If you want ji here, then you put gj here. Okay? And Buchberger's criterion tells us that if you have a Gröbner basis, then when you take this guy and you do long division by your polynomials g, then you get 0. In other words, you get some, when you do long division, you get some combination of GUs with some polynomials here. And the notation has to get a little bit heavy necessarily because you see that this polynomial depends on I, depends on J, and depends on U. And so I'm going to call it F, I, J, U. Okay? We're stuck with that because that's what it is. So this is in the case that we do have a Gröbner basis. Okay? And maybe while you remember how this goes, let's do it in this special case, and that way we will know if we have a Gröbner basis here or not, and that way we will figure out what to do. So remember what we do is we try to cancel the leading guy. Now, of course, that depends on what order we choose. So let's choose lexicographic with x bigger than y. So that this is the leading term and this is the leading term, and we're going to cancel them. So we need to make an x squared y as a leading term. So that means we multiply y by g1, which I'm going to write out, y times x squared, and then minus x times xy plus y squared, right? So this is y g1 minus x g2. And what is this? This is minus xy squared. Okay? And now we're supposed to do long division. We're supposed to do long division. So this guy doesn't fit in here, but it fits in here, right? And so we write this as minus x times g2. Again, let me just write the whole thing out. Minus x times xy plus y squared plus x y squared, right? So remember how this goes. I take s of g1, g2, it's equal to this thing, and then I do long division. So I try to fit this guy into the leading coefficient here, but xy squared doesn't fit into here. It's not a multiple of it. And so then I go and try to fit it here, and I guess this should be a... I see why you guys are all giving me funny faces. So xy squared does fit into here. It's this times y times minus y. And so I get that minus xy squared, and I get some other junk. In this case, it's plus y cubed, right? And then I try to divide this guy. So this is minus y times g2, and then plus y cubed. And now y cubed is my new remainder, and I try to fit it into here, but y cubed is not a multiple of x squared. And I try to fit it into here, and I find that it's not a multiple of xy either, which means that this is not a Gröbner basis, because we have this remainder y cubed. Okay? So not a Gröbner basis. Okay? Well, that's fine, because we know how to deal with that case. If it's not a Gröbner basis, just throw that remainder in, and keep throwing the remainders in until you get a Gröbner basis. Okay? And so that we can do this in an example, let me fix this and make this a Gröbner basis. But I'll make it in a different color to remind you that this wasn't our original plan. But G3 is going to be equal to y cubed. I added it there because I had to, because I want a Gröbner basis. And so I get a relation here, which is what? Y G1, then don't let me make a mistake here, please. Minus x minus y g2, and then minus y cubed, which is g3, is equal to 0. Okay? And so hopefully you see where I'm headed here. Every time that I do this, I get a syzygy. Right? This is a syzygy between g1, g2, and g3. And we continue. Okay? So we're supposed to do this for every pair of polynomials. So we do it for g1 and g3. So in this case, we just get what? Here the leading term is this guy, here it's this guy, so we get y cubed g1 minus x squared g3, and we actually get that equal to 0, right? So let me go over here and write this. Y cubed g1 minus x squared g3 is equal to 0. So far it's looking good. This might be a Gröbner basis. I have to do it for g2 and g3, so now the least common multiple is xy cubed. So I need to take y cubed times, y squared times g2 minus x times g3. And when I do that, I get y to the fourth, right? And then I take this y to the fourth, and I do long division, but y to the fourth doesn't fit here. It doesn't fit here, but it fits here. When I say fit, I mean is a multiple of, right? Which I guess makes no sense at all. Y to the fourth is not a multiple of this, it's not a multiple of this, but it is a multiple of this. And so this is equal to y times g3. No remainder, and that means first of all, this is a Gröbner basis. And second of all, we have a new syzygy. Okay? Maybe I want to write this like this, actually. Okay, and then y squared g2 minus x plus y g3 is equal to 0. Okay. So we concluded two things, that this is a Gröbner basis, and then we have some syzygies. Okay? Well, the beautiful thing, and again, Gröbner bases make life so easy. The beautiful thing is that if you have a Gröbner basis, then these are all the syzygies, and there's nothing else. Okay? Which I hope you're shocked by, because there's no reason a priori to believe that. We got some syzygies, they're very easy, and the fact is that if you happen to have a Gröbner basis, then that's all there is to it. Okay? And so this is the theorem. So let me, the hardest thing about this theorem is to write out in reasonably simple notation. So let me, for each pair of polynomials, write something like this. Okay? And this is going to be this combination, except that I don't want to use g's, I want to use e's, and you'll see in a second why. Okay? So the only reason that I want to do this is an e right here, is that I want this to live. I'm thinking of e's as just indeterminates. Okay, I want one indeterminate for each one of the gi's, and this is going to live in the following module. And again, I'll remind you what a module is and how this works. But if I call my polynomial ring R, then I want this to live in here. So an R module. And so just to be consistent, let me do the same thing here and just take the g's and make them e's. Okay? But the point is that each one of these things we think of as a linear combination satisfied by my polynomials. Okay? And so the theorem is that if this set G is a Gröbner basis with respect to some order, and it's up to you what order you choose, then these polynomials, these elements tau ij generate the module of syzygies. Okay? And what I mean by this is that no matter what relation you find between G1, G2, and G3 in this case, that relation is going to be a consequence of these three. Right? Because the point is that if these three relations are true, then you can multiply this by any polynomial, get this by any polynomial, this by any polynomial, add those guys, and you're going to get a new relation, but that's not really new. It's not giving you anything new. And the point is that these are the three basic ones, and with these three, you can build all the other ones. That's what this theorem is saying. All others are combinations of these. Are linear combinations of these. Okay. This theorem is due to Schreyer. And there's more to say about it, so I'm going to write here furthermore, but I'm not going to tell you. I think today I'm not going to tell you what the furthermore is, but there's something nicer. There's something else that's nice that's also true, so we'll leave this box open and close it next time. Okay. But you see, this makes for a very, very simple algorithm to compute syzygies in the case of a Gröbner basis. Okay. For example, in the case of G1 and G2 and G3, the point is that while you're checking whether you have a Gröbner basis, immediately you're going to get all the syzygies. So do you guys have any questions about that statement?
I guess I'm ready for the reminder what a module is.
Well, let me tell you one more thing, and then I'll remind you what a module is. But again, the way you should think about this statement is just that you get these very simple syzygies, and every other possible combination is a consequence of these three, or these TIJs in general. Okay. So that's the first thing. That's why doing this with Gröbner basis is so easy. Now, what do you do if you don't have a Gröbner basis? Well, we already did the first step, which is make a Gröbner basis. Okay. So 2. If G1, Gn is not a Gröbner basis, then we can use our algorithm for building a Gröbner basis, for extending it to a Gröbner basis, right? Use our algorithm to extend it to a Gröbner basis that starts with the same guys and then continues with some other ones. Okay? Which is what we did over there. Then the next thing you would do is just compute the syzygies of that guy. This is the first step. The second step is compute syzygies of the new guy. So let's call the old guy G, the new guy G prime. So you're going to compute the syzygies of G prime. Okay? But then the last thing that you need to realize is actually fairly easy to see over there. Okay? If we go over here, we got those syzygies between G1, G2, and G3. But we didn't care about G3. G3 was kind of forced upon us if we wanted to have a Gröbner basis. But we didn't care about it. We just wanted the relations between G1 and G2. So what do we do? What we do is we just eliminate E3 from these equations. Okay? Now what's the point? The point is that G3 appeared in a step of the algorithm. It appeared here. And how did it appear? Well, it appeared as some linear combination of the other GIs is equal to something that we don't see, so we call it G3. Okay? And so it's always going to look like this. Something times G1 plus something times G2 plus something times G2 equals something we're going to call G3. And that means that actually we know exactly how to write G3 in terms of G1 and G2. It's y times G1 minus x minus y times G2. And there's nothing multiplying here. There's no coefficient here. And so what we're going to do is just take that equation and say, well, E3 is equal to this, and then I eliminate that variable from the system. Okay. So let's just go ahead and do that. We don't need any of this stuff anymore. So to eliminate E3, we just say that because E3 is equal to because this is one of our relations, okay? Then we're just going to substitute it into the other ones. We get y cubed E1 minus x squared times y E1 minus x minus y E2 equals 0. And then we get y squared E2 minus x plus y times y E1 minus x minus y E2 is equal to 0. And that's it. These are going to be the relations between E1 and E2. Okay. When you kind of sort out what this mess is, you'll see that the relations look like this. Y cubed minus x squared y. Well, now I don't need this anymore. So the relations between E1 and E2 look like this. Y cubed minus x squared y times E1 plus x cubed minus x squared y times E2 is equal to 0. And minus xy plus y squared E1 plus x squared E2. Those things are equal to 0. So these guys are going to generate the syzygies of E1 and E2, of G1 and G2. So you compute syzygies of G prime, and then you say, well, each new GI that appeared out of these guys appeared when computing some S of GA comma GB, and then you got some big thing, and then plus GI, and so you just use that to express GI in terms of the other guys. So express GI in terms of the previous ones. And that way you just eliminate the new variables. So you repeat this until you eliminate the new polynomials. Okay. So this is how you can do this in practice, and it's actually pretty practical. You can do it. It works. Okay. Now, does anybody notice something about that example? Those two simple syzygies. Those are the two simplest relations between G1 and G2. So this one is, I don't know, let's call it A, and this one is B. If I give you a little bit of time to stare at this, you might notice that if you take B and you multiply it by x minus y, you're going to get A. So you have to do it, but so actually A is a consequence of B, which means that you only need B. This is the only, this relation is enough to generate all the other ones. So minus xy plus y squared e1 plus x squared e2 generates all syzygies. Syzygies in this example. Okay. Which, when you look at what the polynomials were to begin with, and you might have noticed that this was the case. What we're saying is basically that the only way to combine these guys and get 0 is multiply this one by this one, and this one by minus this one. So this is basically telling you that there's no non-trivial relations between these two, and actually you could have proved that ahead of time if you had known that ahead of time. But the point is, first of all, that this is a very simple example, but you can do this for more complicated examples, and you will in the homework. But second of all, that the good things about these algorithms is that you don't have to think. You just plug into the machinery, and then out comes what you want. So that's how you compute syzygies. Okay. And I will prove this to you, but to prove this to you, I actually want to prove something stronger, and I want to include this furthermore. And to include this furthermore, I want to tell you about modules, remind you about modules. Okay. And one thing that I would like you to think about is that you could have had a more general question, like, for example, what if you wanted to compute syzygies between something like this? I mean, we computed syzygies between, but maybe I'll keep this so we remember what we just did. But we might want to do this for something more general. For example, I mean, if you think about this, you should think back to what this would be if this were linear algebra, right? If this were linear algebra, then these would be two scalars, and I'm asking you to find basically the linear combinations of scalars that are equal to 0. And that's kind of odd in linear algebra, because in linear algebra what you want to do is find linear combinations of vectors that are equal to 0. And maybe we want to do that in this setting also. Maybe we want to consider vectors of polynomials and find their linear combinations that are equal to 0. In other words, these guys, instead of being polynomials, they might be vectors of polynomials. So maybe gi, instead of being a single polynomial, it might be something like, I don't know, like those vectors, for example. If you think about it, A and B are vectors if you think of E1 and E2 as basis elements. Okay? So for example, maybe you want to find the linear combinations between A and B, right? Maybe, for example, In that example right there, we saw that there was a non-trivial combination, right? And we would have wanted to know that. It would be kind of embarrassing if we wrote down these two are the syzygies that generate, but actually one was a multiple of the other. We don't want that to happen to us. And so we actually also would like to be able to find the relations between these guys. Okay? The relations between the syzygies. In other words, the syzygies of the syzygies. Okay? And to do that, we have to step up into modules. And so that's the plan. But let me make sure that what I wrote makes sense. Given vectors of polynomials g1 up to gm, compute the syzygy module. This where now I allow you to say polynomial times this vector plus polynomial times this vector should be the all zeros vector. Okay. So what about modules? What are these modules? It's very interesting because sometimes you read algebra books and they're very opinionated about this. A book that I cannot remember exactly what book it was, but it basically says any modern mathematician uses modules and not ideals, for example. And people really have kind of strong opinions about this. The point of modules is that there's something very general. So it kind of generalizes vector spaces, it generalizes ideals, but it also generalizes, for example, quotient rings. And that means that, for example, when you want to prove a theorem that's true of ideals, but it's also true of quotient rings, then probably what you want to do instead of proving two separate theorems is go up and say, let me prove it about modules that are a more general thing that includes these guys and these guys. So modules are something that's very general. Because it's very general, that means that sometimes it's maybe a little bit more abstract and confusing, but it kind of pays off. It's a little bit more abstract, but it pays off because it applies to a lot of things. So what's a module? Well, if I want to talk about a module, I have to talk about a ring underlying it. So and let me say it a little bit crudely that basically what's linear algebra? Well, linear algebra is the study of vector spaces over a field. Remember that to have a vector space, you need a field. Every vector space lives kind of above a field. And modules are basically what happens when it's not a field that you have, it's a ring. Okay? So you can think of module theory crudely as linear algebra over a ring. Okay? So let R be a ring. And again, you can do this at a very general level, but for us, we're going to assume that it's commutative, and we're going to assume that it has a 1. And actually, generally, we're going to assume that it's a polynomial ring. But let me not commit to that in this definition. But generally, you should be thinking that R is, I'll even just write it out. Generally, R is going to be just polynomials. So usually for us, R is a polynomial ring in variables over a field. Okay. So what's a module? So we say either R module or module over R. Is, and again, I want to write something that is psychologically correct, but you need to be very careful about. This is not the definition, but it's a vector space over R. This is a good way to think about it, but what is it really? Well, what is it mathematically? What do you have in a vector space? Basically, a vector space is something where you have an addition, right? And so what that means is that you have, let's call it M, okay? is an abelian group M, meaning that you have a way of adding, subtracting things in M. But then the other thing that you have in vector spaces is the possibility to scale vectors by things in your field. And here you're going to allow yourself to multiply by things in your ring. Okay? And this is called an action. Okay. So this is a rule with which you can take an element of your module and multiply it by an element of your ring and get back an element of your module. Okay? An action of R on M. And again, the way that you should think about this is a way of multiplying by elements of your base ring. Okay. But you need to satisfy some simple properties. For example, well, this is a ring, and so it should be compatible with the ring structure of R. So that means that if you multiply by R plus S, then it should be the same as if you multiply first by R and then by S. If you multiply times RS, then it should be the same thing as if you first multiply by R and then by S. And that tells you that R is compatible, sorry, that this action, that this multiplication is compatible with the structure of M. Now, because I said that my ring has a 1, I also want this action to be compatible with that 1. And what that means is simply that when you multiply by 1, nothing should happen to you. So that's compatibility with the structure of R, but then also you have to be compatible with the structure of M, because M is an abelian group, so it has a way of adding. So when you multiply by an addition like this, then it should be the same thing as if you multiply like this. Okay? And then you kind of put the usual qualifiers for R and S in the ring and M in the module. This is for R and S in the ring and M in the module. This is for all M in the module, and this is for all R in the ring and M and N in the module. Okay. And it's always hard to remember what all the different things are, but I think that it's a fairly safe way to think about it in this way. So it's a set where you're allowed to add things and you're allowed to multiply by elements of your ring. Okay. So what are some examples? Well, the reason why module theory is so rich is because there's a lot of examples and a lot of very important examples. So examples, well, like I told you, the first thing is if the ring happens to be a field, then the definition of R module is exactly the definition of a vector space. But this is too simplistic for us, because for us, generally, the ring is not going to be a field, it's going to be a polynomial ring. Okay? But then for any R, there are several examples of modules. So for example, a simple one is just R to the n. Just like for a field F, you can make the vector space F to the n. For a ring R, you can make the module R to the n. You can clearly add things in R to the n. So these are just n tuples, right? They're vectors of length n with elements in R. You know how to add these guys, and I only need to tell you how to multiply them, but there's kind of no choice there, right? If if you want to multiply a vector in R to the n by an element of R, then the natural thing to do is just multiply component-wise. And the reason you can do this is that R and R1 and all of these guys are in your ring, so you know how to multiply them. Okay? So that's an example. Another example is an ideal of your ring. Okay? How are you going to multiply things? Well, you know how to add things in your ideal, and it's important that if you add two things in the ideal, you stay in the ideal. This is one of the properties of the ideal. You also need a rule to take elements of your ideal and multiply them by elements of your ring. Right? So given an element R in my ring and an element I in my ideal, I should tell you how to multiply them. How are you going to multiply them? Well, again, you don't really have a choice because your ideal is a subset of your ring, and you already have a multiplication defined there. And so it just makes sense to be it's kind of an empty equation, right? Now, the thing that's very important is that this is supposed to be an action of R on M, meaning that if you multiply by something in R, you should stay in M. Okay? But then you see that this is safe because when we have an ideal, so when we multiply by something in the ring, we stay in the ideal. Okay? So this works because I is an ideal. So that's another example. And another example is that if you have some ideal, then actually you can consider the quotient ring, R mod I, and that's also going to be a module. How is that a module? Well, the elements of R mod I are cosets, right? And you know how to add cosets, and you know that the sum of two cosets is a coset. We need a rule to take a coset of I, which maybe we can call A plus I, and multiply by a ring element. But again, the natural thing to do is to consider the coset of our A, and this works. Okay? For R in the ring and A in the ring. So that means that if you prove a theorem about modules, then you have a theorem about all these circumstances, and that's why I'm telling you that if you have a theorem that happens to be true for ideals and for quotients of ideals, then probably the right level of generality to prove it is modules. Okay. So that's the definition, that's some examples, and now we should talk a little bit about what modules look like. What's the difference, basically? Why do we bother to do this if we already know how to do linear algebra? Okay. Well, over fields, this is just linear algebra, right? And over fields, actually, we understand this very well. Every vector space is characterized by a single number, which is called its dimension. Right? And if you know what dimension your vector space has, then you just consider a set of that dimension, a set of that size, make that a basis, and that's going to be your vector space. Okay? And every single vector space is isomorphic to f to the e for some set e. So vector spaces are very simple objects, actually. You just need to know their size. Okay. What else? Every minimal generating set has the same cardinality, and it's the dimension, right? Furthermore, so that we have a name for this, right? This is called a basis. And if you consider the elements of a basis, they're fully independent of each other. Okay, so the elements of a basis are independent. Okay. And over modules, you can decide whether you think it's more. I mean, it's more complicated, basically. So you can decide if that makes it more interesting or scarier. I think it's more interesting. So over modules, these things are not true. Not true. Not true. Not true. Okay. What's a generating set? I should first tell you what that is. So, a subset of the module generates it. As a module, as an R module. If everything in the module can be written as a linear combination of things in A, right? What's a linear combination? Well, these guys are vectors, and these guys are scalars. That's the way you should think about it. So your scalars are in the ring, and your vectors are in your module, but actually they're supposed to be part of the generating set. Okay. So let me give you a quick example of this. Let's consider the polynomial ring in two variables. And let's consider the module, which is the ideal of polynomials of degree greater than or equal to 2. Well, actually, that's not quite an ideal. It becomes an ideal if you add the zero polynomial. Okay. So if you add two things of degree greater than or equal to 2, well, you want to be a little bit more careful then. Let's just consider this ideal. Okay. Okay. So this is the generating set by definition. These three guys generate. Okay. But you can see that this is a minimal generating set in the sense that, for example, if you take these two guys, you can't generate y squared, right? Because you can only generate multiples of x. And if you think about it, these guys are minimal generating set. Okay? Minimal generating set. You need all three. Okay, but this is a minimal generating